now get into the issue of free monoids, which will hopefully build on some of that intuition, but take it further. There's some things it won't need from this exposition that we've just seen. So one of the motivations for dealing with free monoids is in fact, the whole adjunction context with which I've introduced this topic, right? We have set, and we have this adjunction from set to monoids. And free monoids crop up in this context. Each set is mapped to not just any old monoid, but a free monoid. And in the adjunction, we're reasoning about the hom sets. We're reasoning about these morphisms in each of these categories. So the rules for adjunctions guarantee this isomorphism. So if we pick any old set S, and we pick any old morphism M, any old monoid M. So any old set and set, any old monoid M in the category of monoids, this category M, then this property has to hold true. That's guaranteed by the rules of adjunction. Okay, so if we map S over to LS and we consider the monoid homomorphisms between that mapping down to M, those have to be on a one-to-one basis with and a bijection with in an isomorphism with the homomorphisms you get from mapping M over to set and going from S to M. Okay. Now here over in monoid, the things linking up LS, this mapping of S over, and the object M which we picked, the monoid M which we picked, the arbitrary monoid, those were homomorphisms. Over in set, these morphisms are what? What are morphisms in set? They are, it begins with F. They are
functions.
So they map each element of the sort set S to some particular element of M. And these can be all sorts of functions of a most unusual and sometimes unseemly type. I don't know. I've never met probably a function I didn't like, but I guess it could be unseemly. This is an interesting and almost provocative statement that you pick an S, you pick an M, and I will guarantee you this correspondence. Now, the other thing that's part of this, though, is the very particular mappings, the adjoints, which are a key part that guarantee this. So it has to be very specific adjoints. The adjoint going to the left, mapping from the set to the monoid here, LS, is the free functor. So it maps any old set to be a free monoid based on that set, and we'll see what that is. But the other functor is the underlying functor. It takes any old monoid M you've picked, and it extracts the set, which is part of that monoid. So any old monoid is associated with some set. Here we encoded that set in a set of morphisms, but here we're abstracting over how it's encoded. It's just some old set there, whether it's encoded in hom set or whatever internally, it doesn't matter. It's some old set. It has some set as part of the monoid, and we extract that, and that's what RM is. Okay. So we're extracting, that's the underlying functor, the forgetful functor. And we write the adjunction like this. Monoid is left adjoint to set. Okay. This is called the left adjoint functor, and this is the right adjoint functor. Okay. Now, last time I said, look, we talk about a free monoid, but if we really start to buckle down and get down to brass tacks and think about think about how free can a free monoid be, we find that there's actually some hidden constraints. We find that there's some secret shackles. Not so secret, but there's some shackles that maybe aren't obvious immediately. So let's imagine trying to build up as much freedom as we can here. So we know we have to have identity morphism. That's given to us. That's handed to us by the rules of categories, and that's what we're dealing with here. We're only gonna, for a free monoid, we're dealing. It's free not in the sense that it doesn't cost any money. It's free in the sense that there's minimal restrictions on it. There's only the restrictions attendant upon being a category. And so we're trying to figure out what things are allowed in the rules of a category for a monoid. And one thing we know we have given to us for any category is we have an identity morphism. That much is given. So we have to be dealing with that. And I actually even haven't put that in here because it'll be incredibly numerous if I put every combination with identity in. But we know that it's a given that if you combine identity with any other morphism, you get that other morphism back. Okay, so our hands are tied on that, right? We can't do anything about saying for my category, my free monoid identity combined with F is gonna equal G. No, we can't do that. We have to have identity with F gives back F. Okay, if we have a morphism and we combine it with identity from the left or the right, we have to get that same morphism back. Okay, but we have some latitude here. For example, maybe we have a morphism F. How if we combine that morphism? Well, we know we combine with identity to get it back. How if we combine it with itself? So we had sort of F combined with F, right? And if we think about it in a categorical way here, it's F after F, right? With composition. Again, here we don't have to think of it in this way. We're abstracting over what it is, but let's just think about it that way, for building our intuitions with this as a category. So F combined with F, well, we don't have to have that be identity or have to have that be F. There's nothing about categories that say that. So we'll give it a new name, G. Okay, we're gonna call it G. Great, we're gonna call it G. We're being minimally restrictive. If we have the opportunity to call it something different, we will. Unless it's forced upon us, we don't reuse things. So now we have F and G. Great. Okay, so suppose we combine F and G now. Well, if we combine F and G, is there anything forcing us to give back something we already have, like F or G? If you think about it, no, there's nothing that forces that to be G. It doesn't force it to be F. So we'll call it H. Okay, great. So now we've got G and we've got H, and the road is open in front of us. The sky is wide open. We are in Saskatchewan after all. So we got H. Great. But now let's deal with G and F, because remember, that's not necessarily the same. G and F. Well, okay, now wait a minute. Now, you might think we could call that I, but hold your horses, because F we know is F is kind of our building block. F. G we know is F combined with F. So if we have G, we have basically G being FF. That's what it was. It was defined as at the composition of F and F. And now we're combining it with F again. And we know by the rules of associativity that this needs to be the same as F combined with FF. And guess what this is? Anyone recognize what's F combined with FF? It's what?
H.
F combined with F combined with FF is H. Yes, it is H, exactly. And it's because FF is what? G. FF was G. We combined, G was F combined with F. So that's G right there. So FG, by the rules of associativity, if we have to be able to forget where the parens are without worry, we can erase the parens without worry that it's ambiguous. We need clearly F combined with FF to be the same as FF combined with F. And FF is none other than G. We combined F and F to be G. So this is saying FG equals GF. So we're going to have to reuse H. We can't allocate a new name for it because it's got to be H by the rules of associativity. If we combine F, okay. Now we're getting some constraints imposed by us by the rules of category. Now let's consider the rules of being a category. Now let's consider G. Okay, we got G. We had allocated it before. I'm speaking like a computer scientist here. Okay, so G combined with G. Is there anything that forces it to be anything else? To be something else? Well, we have if we think about the associativity side, this is kind of like FF combined with FF. There's nothing that particularly requires a separate thing, so we'll call it I. And as you go down through this with kind of similar reasoning, you can end up, recognizing things that have got to be the same. For example, F and H is just F and then FG here, because H is just F after G. And so we've by associativity, we have to be able to move these things. We know FF is G, so we know that this has to be the same as GG, so we have to reuse I. And I think you see kind of the type of reasoning. We're going back and looking at these definitions of earlier ones in terms of what they represented. And the associativity rules are the ones that keep on getting us. They keep on imposing these restrictions. They keep on forcing us to reuse things to be a legit category. The fact that we have to be able to erase these parens without any ambiguity forces our hand and forces us to reuse some things. So I've shown in black all the things which can be newly allocated, and the things in magenta are things that we end up reusing. We have to reuse because of rules of associativity. And what you end up finding is that the rules of associativity do constrain you actually a fair bit. In order to be a legit category, we can't allocate, just say willy-nilly M combined with Z is going to be, omega or something like that. It's we've got to actually accord with these rules that bind us quite tightly in terms of associativity. Now, the thing I didn't get to last time, but which is a key point, is if you go through this exercise, and it's a fun exercise to go through, at least in my definition of fun, what you end up realizing is, it's all about the associativity, and you're always unpacking things in terms of their earlier definitions here. And the earlier definitions, if you really unpack them, what you get down to more and more, if you go to, for example, K is G and I. What is G? Well, G is F and F. And what is I? I is G and G, and each of G is F and F. You're getting different sequences, all composed of this element F, okay? Sort of the primordial element, F here, the primordial non-identity element, F. It all gets unpacked in terms of sequences of F. And if you go through this, what you find is that the things that were newly allocated, G, H, I, J, K, are none other than successive sequences, unique sequences of this primordial non-identity element F that we started with, which we started. And that should give you pause for thought, because all these other ones that ended up being reused, that's just because we are putting parentheses in different places within these sequences. So maybe we had, F and then FF and then FF for this one, or another one we had FF together and then FF and then F, or maybe we had FF and then F and then FF. So these other ones were kind of arbitrary parenthesizations that, because of associativity, okay, fine, it's just the same thing. Really, this is the essence of it. It's the sequences. The sequences are the elements being named anew in this monoid. In this monoid, in this free monoid, the elements of the free monoid are nothing other than these sequences. And I'd include in here F itself, and I'd include in here the identity as the empty element. After all, the identity combined with anything else gives itself, which is the same as concatenating sequences. So what we're seeing actually emerge from this, from a free monoid, is composition within this, or monoidal product of two things, of two morphisms, basically consisting of the concatenation of the sequences associated with them. And in this case, it's unary sequences, it's sequences of this F thing. Okay, so if we have a monoid, so here, this minimal free monoid, it's kind of one we tried to build up to develop our intuitions about what's free in it. We found the things that are free, that were free to be different, are each possible sequence of this kind of primordial non-identity element. But in general, ladies and gentlemen, if we think about this mapping, the free monoid for a given set, the free monoid corresponding to that set, is going to use, as it were, and I'll speak informally using the term here, as generators, for it, the elements of the elements of S. We used F as our again, informal generator here. And we got sequences of Fs as the elements. If we have if we have a set S and we turn into a free monoid, what we're going to get out we're not going to start with just F. We're going to start with each element of S as being kind of a primordial element that can be combined in these sequences, and anything can be reduced ultimately to some sequence of elements of S. And therefore, any set S gets mapped into a monoid who's a free monoid, whose elements consist of sequences of elements drawn from that original set S. So maybe the set S here was, and I thought I might have a nice illustration of this, but maybe the set S is 0 and 1. And again, I said it earlier, but I'll say it again in this context because we're spiraled back to it. If S is the set 0 and 1, then we're going to have elements of the free monoid LS be all possible sequences of 0 and 1, all possible binary sequences, including the empty one. if S is just zeros, we'll have all possible unary sequences. That's what we add here, right? If S is three possible things, three elements, we'll have all possible sequences of those three elements. So, if those three elements are ABC, we'll have, we'll have empty sequence, and then we'll have A, or we'll have B, or we'll have C, and then we'll have, AA and AB and AC and BA and BC, etc. Sequences of all different lengths of those. Okay, so here we have this for a set S, and I've called it. I should have been more careful here. This is actually a bit screwed up. So this should really say if we have a S, a set S, L. So I'm just going to accord with what's in the diagram to avoid confusing you. Sorry about that, but basically, if we have a set S, LS consists is the free monoid on set S, which can be expressed as S star. And some of you may recognize this. Where have you seen this cleaning star or cleaning closure of S? Where have you seen this before? It's actually featured in 214 of all things as part of the teaching there. It comes up in what?
Regular expressions.
Regular expressions. If you have a set, and you say, take the character, digit star, right? Sometimes the regular expression languages have a special encoding for digits, and you could, \D or something, star, right? It just means any possible sequence of zero or more of these. That's exactly what this is. This is the from the free monoid. So here, this equivalence, it bears noting that for the monoid, this free monoid, the empty sequence serves as E. Concatenation of two sequences serves as monoidal product. And the identification of the elements as sequences, ignoring whence they came, for example, whether they were built up originally as F tensor G, then tensor H, or whether it was built up as F tensor G tensor H. Regardless of that, we're dealing with them as sequences. We're imposing, by virtue of abstracting away from how they're built up and just dealing with them as sequences, we're imposing associativity. We don't care about how they're built up. All we care about, we don't care where the parentheses are or were. All we care about is the sequence that emerges, right? And as long as it's the same sequence, it doesn't matter how it built up. That's what we're capturing over here, and that's why that's a monoid. So it's a very natural mapping. Now, what this means, though, and this will start to hopefully start to build some intuition for this next stage, is you could start to understand this equivalence better. So, the quandary that I think Bartosz Milewski explains quite well here, the kind of paradox that seems to apply here is that, look, on the one hand, you have this category set, right? And remember, I said for an adjunction, you can pick the set S, you can pick M, and I guarantee that this is the case. And this is a strong guarantee. It's saying that if you give me S and you give me M that you've picked, M is is a monoid and S is a set here. I can guarantee you that if S is mapped over into monoid, that the homomorphisms between LS and the M you picked have a one-to-one correspondence to the morphisms, that is the functions between S and the mapping of the M you picked over to set by just forgetting its monoidal structure and just taking it set. It's a one-to-one correspondence, and you could be excused for saying, how could that possibly be? Look, sets here have incredibly numerous numbers of functions between them. They have functions that are nasty ones in terms, as well as really nice ones. They have all sorts of weird functions that do strange things, and that don't have seeming rhyme or reason associated with their rules. But meanwhile, homomorphisms are very very rigid, or very it's not rigid. They're very structured quantities. They preserve monoidal structure. They're very disciplined about preserving that structure. And yet we have this isomorphism between them. And how could that be? It seems at one level as a paradox, but I would argue there's good intuition here. And I'm going to try to help you build up that intuition, and we're going to look at some particular examples, and you'll see why this has to be the case, hopefully. You'll see where it comes from. Okay, so the first intuition I want to build up is, look, while this might seem implausible, well, it might seem that this is a very narrowly defined set, and this is a broad set. You have to realize that S gets mapped to a free monoid. S doesn't get mapped. And you pick the S, any one of them is going to be mapped to free monoids. And free monoids are not any old monoid. Free monoids have a very particular structure. And they have a structure that's quite expansive, if I could, or they have elements that are quite expansive. You may have a set that has one element, one single element, and it gets mapped to a free monoid that has unlimited number of elements. I mean, it has arbitrary number of, it has a countable infinity of elements, right? It has every possible sequence of that element. It has empty set, it has the element, the singleton sequence, it has two things of that, 3, 4, and so on, without bound. So a given set might be very small, but it gets mapped to an unbounded free monoid set in the free monoid to which it corresponds. So for a given set X, L of X can be far larger than X. Now, a second thing to realize, though, so that's a key thing. We've got tons of elements being generated out of here. That surely gives us a certain bit of latitude, right? In thinking about this. Now, secondly, remember that M here, this isn't necessarily to build intuition why this has to be the case, this isomorphism, but it's just a good reminder. M could be any old monoid. You pick the M. So you could give me a free monoid, or you can give me a non-free monoid, and most monoids are not free. Most monoids have a lot more structure than free monoids, and so it need not be a free monoid, all right? But the sequences in LS can often be kind of mapped to that monoid in a number of different ways. And as we'll see, those ways are in one-to-one correspondence with these ways. Okay, so let's see that. Okay, so here's the thing. We said it here, but I'll say it again. Okay, so maybe I have a bit of a better explanation here, but so if we have two sets X and Y, let's think about this. Okay, suppose you have a set X, and you have a set Y, and you're considering all the functions X to Y here. Okay. How many such functions do we have? Well, it turns out if X and Y are sets, you have this many functions. The size of set Y to the power of the size of set X. Now, you may think, well, it's not obvious, and you may forget which X is in the exponent, which is in the base. But humor me this. The way I actually remember this very, very readily is I don't just memorize its Y, Y at the bottom, the codomain at the bottom, the domain at the top. Well, after a while, you develop that intuition. But no, you could think, look, okay, imagine Y is just 0 and 1s. It's just binary digits, right? X is mapping from each element of X to a binary digit. Surely we have like 2 to the something number of possibilities, right? Because each of these source ones can be mapped to a 0 and 1. So we're going to basically get out sequences of binary digits, and there's 2 to the so many possible sequences. So it's got to be, if Y is binary digits, is of size 2, the 2 has to be in the base here. It's not in the exponent. And that's the way you can remember, okay, this thing is in the base. But there's these many functions, and that holds true if Y is binary or not, right? Encodes 0 1s or encodes a huge number of different possibilities. This is the number of functions, okay? And it's look, each of these mumble. So this should have this should be UM here. Sorry. So each of these elements of X can pick any of these elements Y, right? This is the Y set is so unrestricted. I mean, it can, or set functions and set are so unrestricted. They can pick for each X value of X, they can pick any value of Y. And therefore, for the first of them, we have maybe Y is 2, right? And so for the first element of X, we have 2 possibilities. And for the second element of X, we have those 2, but if we consider also the second element of X, we have 2 times 2, because the second element of X could be mapped to either 1, 2 as well. And the third element of X could be mapped to any of the Y's as well. And so for each element of X, successively, you're multiplying by 2, right? You're multiplying by, in general, the cardinality of Y. So if Y is of size 2, you're multiplying 2 times 2 times 2 times 2, X times, X count of things in X times. For every possible value, for every element of X, you have this multiplication. And that's why another reason you could see that. So the sets, these functions don't offer any particular structure. You can see it right there. I mean, look, you can pick any value of X to be any of values of Y, without constraint. There's no structure really that's being captured there. So we have this this thing here. Now, oh, you know what? Okay, I should have, no, so this shouldn't have been changed back, because I should have noted here. Okay, so look, here we're going to be dealing with this mapping, and we're going to be reasoning about the cardinality here. Okay, so let's reason about S to Rm. What is Rm doing? Well, for a monoid, an arbitrary monoid, you picked, all the underlying functor is doing, all the forgetful functor is doing, is extracting the set from that monoid. Okay, and so if this monoid over here is defined to be X with this tensor product E, if that's what this monoid is, if it is associated with subset X of its elements, whether it's encoded or in morphisms or not is irrelevant. If it's some set X of elements, Rm is going to be X, right? Yeah. So I said R, but I should have said U here. In any case, it's the same thing as U. U equals R. Okay, it's the underlying functor, the right functor. Okay, so this is of size this. I mean, by the same argument I just gave, these functions have, for each element of S, you have to pick an element of UM, right? And UM or RM is X. Okay. So we know that. We know all about functions between things. We know there's that many because there's no structure to capture. Okay, now let's consider mon. This is a trickier one. Okay, so we got this LS. Oh man, we got this free monoid associated with S. What is that? What is the free monoid? What are the elements of the free monoid associated with S? Can anyone say? I said it earlier. What are the free elements of the free monoid associated with S? What are the elements associated with the free monoid that's created when we map S over into LS? What is LS? The elements of it are what?
Is it S?
Are what?
S. So the elements in S.
Oh,
one.
Okay, but they're all sequences of those elements, right? This is what I said earlier. So LS, if we have a set S, LS is the free monoid on set S, consisting of elements that are strings of sequences of elements from S. So yeah, I was a little bit ambiguous in the way that I asked that, and it's a terrible thing in English. The word element, the elements of the sequences are from S, but LS is a monoid whose elements, in terms of being a monoid, each monoid is associated with a set, and that set has in it one element for each possible sequence of items from set. So if S is again 0 and 1s, LS has as its set the empty sequence 0, 1, and then 0, 1, or sorry, 0, 0, 0, 1, 1, 0, 1, 1, and then 0, 0, 0, 0, 0, 1, and so on. Yeah. So here, we have elements of LS as a monoid that are all sequences of elements drawn from S. I don't know why I said unary. That's all sequences. It's horrible. So FS, oh man, or LS. I'm gonna call it. Oh man, okay, this is bad because here I call it LS. I'm gonna call it LS just to lower confusion. And now I'm in trouble because it appears a couple more places here. The reason it's the same thing is because the left adjoint is the free adjoint, and so sometimes I call it L, sometimes I call it S, and I'm a bad boy. Okay, so this this set of homomorphisms are going to need to map from the monoid, whose elements are all sequences of elements drawn from S, down to M, right? And each of these elements of the possible elements of S, so each of these elements from S which are mapped over here. These sequences are of those elements. So if we had 0, 1 here, we'll have binary sequences here of 0 and 1s. If we had just 0 here, we'll have unary sequences of just zeros, including, in both cases, the empty one. If we had if 0, 1, 2, we'd have sequences of 0, 1, 2s here. And every length from 0 upwards, right? But here, each element of a sequence, it turns out, can be mapped onto any element here drawn from this set M. So when we're mapping with a monoid homomorphism, basically what we're doing, observing associativity and so on, is we're mapping each possible element of the sequence. Those elements are from S. Like we're mapping 0 and 1. If S is 0 and 1, we're mapping 0 to some element from M, from the set X in M. We're mapping 1 to some element from the set X in M, from the same set. You picked M, but it has some underlying set associated with it, X. And each of these elements of LS, which are the elements of S, is being mapped to a particular value from that X. Okay, that's really what's going on in the homomorphism, and by so doing, we basically can dictate how the whole sequence, by dictating how each element of S is mapped onto the elements of M in X here, because that's what X is, it's the elements of M. By dictating for every element of S, then we can figure out how to map the whole sequence down to M, because the whole sequence will just be the monoidal combination using this monoidal operation in M of all those mappings of the individual elements of the sequences, which were all drawn from S, the individual elements. So really, that's the essence of what's going on here. And because for each of the elements of S, which are the elements in the sequences LS, we have a choice of X possibilities for how to map it. 0 could be mapped, maybe X down here is ABC, and S is 0, 1. So there's going to be here a homomorphism which maps 0 to A and 1 to A. There's going to be another one that maps 0 to B and 1 to A. There's going to be another one which maps 0 to A and 1 to B, etc. And so for each of the elements of S, each and every one of them, I have free reign to pick any element of M, of the set associated with M, which is the set X, to which to map it. So I have two possibilities. Well, in that case, I have three possibilities for 0. I could map it to A, B, or C, right? 3 possibilities. I could map 1 to A, B, and C. So there's a total of 3 times 3 or 9 possibilities. And in general, for each element of S, I have X possibilities. So I have X to the S different possible mappings, which is exactly the same. As you have obtaining over here and mapping from this into that. And the reason this all works is because you have the monoidal operation down here on M, which puts all these, if you know how to map each particular element of these sequences, all of those elements were drawn from S, then you know how to map the whole sequence by combining it up, by folding it up using this monoidal operation here, and you'll get a mapping for the whole thing. Okay, so so let's go through a few examples of this if we could. So here. So we're going to look at this for some particulars. So suppose S is some singleton set, just some set with a single element in it. We'll call it star. And maybe M is a singleton monoid. You gave me some low balls. You picked S to be particularly simple, and you picked M to be particularly simple. Ooh, that's nice. That's easy. Well, okay. So let's do the set one first. This is pretty easy. Look, from the set one, we have one element in this set, and the underlying set of M only has one element too. That's what this is. M is this set in it. It's only one element. So all we have is one choice. There's one choice to rule them all, right? There's one possibility. So the homomorphisms here, or sorry, the functions are, there's only one. It just maps the only element here to the only element there. That's just, the function has no choice. Okay. For the monoids, here we're going to have monoids consisting of unary sequences of stars. That's what this is. It's a unary sequence. The free monoid LS is unary sequences of stars. And for those unary sequences, we actually are going to need to map them down in a way. We're going to need to have a homomorphism between that and this monoid M, which happens to have a single possible element in it too. And what that means is the empty sequence here, which serves in this free monoid as the unit, needs to map to the unit here. Great. And then any combination of things here through concatenation needs to map to the corresponding monoidal product over here. Well, it turns out that there's only one possible function which does that. I mean, after all, it maps the empty to the empty, and it maps everything else to the empty too. Maps all the possible values from set, of which there's only one to the if I said empty, it should be to the unit here. The single element. So there's only one. Okay, let's go into something a little bit more interesting here. Suppose that we have here S being 0 and 1, okay? And we have M being this kind of trivial monoid. And how many sequences are there from S to RM here? Well, here we're going to have 0, 1, and RM is just going to extract this set from M, from the monoid. That's what RM is. It's the underlying functor. It's a forgetful functor. It sucks out the set here. And so what this is going to map is 0, 1 onto a single element here. It's a singleton set. And there's no choice. You have to map 0 to that single element. You have to map 1 to that single element. It's there's no choice in the matter. So there's again only one possibility. Now for the monoid, now you're going to have all sequences of 0 and 1s, but we're going to need to consider homomorphisms of those sequences that map over to M. But again, we have basically zero choice in the matter because M is only a single element for our case. It is just a single element. So we're only going to have one choice. And there's only one function which maps any old element 0, 1 or any old sequence to the single thing. It can't go anywhere else. Okay, let's take it a little bit more further, but still staying basic. So let's look at a case where S is a single element, but where M is actually this monoid, which has plus mod 2. That's kind of interesting. And it has 0 and 1 as its possibilities. Okay, so we have this being one thing. Now we hit it with the free functor. We hit it with the left functor, which is the free functor, and it maps to sequences of that single element. So these are unary sequences now. And those unary sequences now need to map down. They need to map down to the elements of, they need to map into M. So the empty one needs to map into some unit in M, which will be 0, because 0 plus mod 2 something else is that something else. And then every other thing here also has to, we have to have a homomorphism. So any combination of things here has got to map over to the results of mapping over the pieces of that being combined and taking their combination here with plus. And if you think this through, this mapping G, which let's consider this called G, a homomorphism here, it can really do one of two things. It can map everything to 0, or it can map empty to 0 and a single character to 1. And basically it's going to be counting up the length mod 2, because it's going to be it'll be combining those together to compute the length of the whole sequence, if we were seeking to do that. But basically we have two choices here. We can either map everything to 0, or we can map empty to 0. That has to go to 0, and then a character, the characters that are in these unary sequences to 1. And that would be a homomorphism, if we were to do that as well. So here we can end up having in place two possibilities in both cases. Now let's consider 0, 1 on both sides. 0, 1 here, 0, 1 here. So we have a monoid that has 0, 1 as the possible things, and we have S as 0 and 1. So let's reason this through. Well, for set, each we're just mapping 0, 1 to 0, 1, because we're mapping S, that's 0, 1, to the set of items from the monoid, which is also 0 and 1. So pretty straightforward. We can map 0 to 0, we can map 0 to 1, we can map 1 to 0, we can map 1 to 1. We have basically 4 possible choices. Now, for the monoid side of this, it's a little bit more tricky with the to think through, but basically to have a monoid homomorphism here, we're going to consider the homomorphism G. We know that G of the empty sequence has to equal 0. And we know that G of A concat B has to be G of A plus mod 2 G of B. That's just the mod 2 thing here. So one way we can get this is if we map 0 to 0. Well, okay, we have to map we have to map empty to 0. but we have some latitude now. We can map zeros. These are binary sequences. Since we have 0, 1 here, these are binary sequences over here. So we could map 0 to 0 in the monoid, and 1 to 0, in which case everything gets mapped to 0. That's maybe not so interesting as a homomorphism, but it's always a possibility, and it preserves this property. We could map 0 to 0 and 1 to 1, and in a way you could think of this as related to counting ones mod 2, but it's a consistent homomorphism. We could map 0 to 1 and 1 to 0, or we could map 0 to 1 and 1 to 1. So we have 4 possibilities. Each of 0 and 1 can be mapped to each of these ones, which is 4. And the same thing, carries through. There should be also 8, 2 to the third such maps. And in general, if you have some set X and some set Y, by virtue of what you need to do to adhere to the homomorphism property here, you have Y to the X possible monoid homomorphisms, and you have Y to the X possible maps between the corresponding sets. And that gives us this equivalence. So free monoids, have this isomorphism, which on one hand seems outlandish, but if you really understand what it means to map a free monoid down to an arbitrary monoid, you can get some feel as to why it gives the same combinatorics as it does over here in set. Okay, now in my closing minutes here, though, I want to, a key point here, though, is that I want you to carry away from this, because we've covered a lot. Free monoids for a given set are sequences of elements drawn from that set, where those sequences are of length 0 and above. They're all possible sequences. And you could think of each sequence as sort of being a combination of the elements of X, where we give each such combination a new name, but we capture associativity. So we don't willy-nilly create new sequences that only differ by where the parentheses are. We're true to the needing to achieve associativity. So it's really distinct sequences of values from X, and that's what is associated with a free monoid. I'd like to talk very briefly about 2 other constructs, though, that will be laying the groundwork for what's coming up, and hopefully whet your appetite for why, while we will be nominally leaving monoids to discuss monads, in fact, monads will be there monoids will be there behind the scenes with monads, and we'll make that connection explicit. But only that, we will further have monads or monoids that we'll be revisiting for their applications with free applicatives and with symmetric monoidal categories and modeling type needs. But first, I want to introduce something called a Bi-Functor. Okay, and a Bi-Functor will, in some sense, presage the use of profunctors as well, which are sort of more interesting yet. But a Bi-Functor basically is a mapping. It's a functor, but it's a mapping from a very particular category to another category. So we're going to focus on Bi-Functors, which are from for a category C, which are from C cross C, which is a category where each object is the monoidal product of some object in C. is just a pair of objects from C, any two objects from C, and where the morphisms are pairs of morphisms from corresponding objects in C. And a bifunctor is going to map that into C itself. And some definitions are given here, but basically for morphisms, those morphisms are going to go from the corresponding products of their pairs of their sources to pairs of their targets. Now, the reason I want to introduce bifunctors is because they are key for the definition of a monoidal category. And you can hear more about this at this lecture 15, where David Spivak gives a very nice introduction to them for Programming with Categories course. We talk about monoidal categories having being categories which have a monoidal structure. And it turns out there's different levels of strictness with which we can define this. This is defining a strict monoidal category. But here we're going to have this monoidal product, which is a functor. It's a bifunctor. And I should probably say Bi-Functor, okay? So this is going to be, for a category to have a monoidal structure, there needs to be, it has to be equipped with or accompanied by a bifunctor, which takes pairs of objects in that category and maps it to a resulting object that is the result of their monoidal combination. So it's combining objects to yield another object. That's a little bit different from what we saw earlier, but it also has to have a monoidal unit, which basically is an object in C. And we like to define that in category theory as a functor from the categories one object into C, which basically picks out exactly one object in C, because there's different functors that would from one to each possible object in C. And so this is a kind of fancy way of saying it's an object in C, but saying so in a way that focuses on the relationships, the functors here. And it has to observe these properties. So this functor, which maps from C to C, from C cross C to C, from pairs of objects in C into C, and pairs of morphisms in C into a morphism in C, has to observe associativity and unitality. So it has to, if you combine with this special monoidal unit any other object with this bifunctor, you get that other object back in whatever order, and you have to have this associativity. Now, there's again different levels of strictness for this, and they have to do with to what degree you have equivalence in these things, or to what degree you have, for example, natural transformations. And one of the things we'll be coming back to for applicatives are lax monoidal categories and lax monoidal functors. And it turns out that defining monoidal categories lets us define monoidal functors. And then they have to observe some laws which basically impose, which basically are associated with these constraints. These have to commute. You have to be able to go around these in any order, and I won't go through them now. Now, this is a thing I wanted to get to, though, because monoidal categories provide us this rich language that's really useful in two very important areas of applications. Number one, by allowing us to reason graphically about models of a situation. And this is from Brendan Fong's lecture, which I'd invite you to watch. Here's the link to this particular time. But basically, he maps out this relationship between some of the things we've been seeing, like pre-orders. We're going to get to monoidal pre-orders. And in fact, there's a video for them if you want to kind of be able to go on that side of it. We kind of went with monoids and categories and monoidal categories, right here with monoidal categories. But basically, once you get to this level, you can draw out these things called wiring diagrams, and reason about them in a way that's completely mappable to, defined with, an isomorphism to operations on a monoidal category. So you can write out these components as in these monoidal operations. So, for example, F here is going to be operating on the monoidal product of Y and Z. Okay, and Z here will be operating on something that's X, monoidal product of X and B here. And it turns out that each of these other things, like monoids, can also be illustrated diagrammatically. And with categories, it's kind of like that, except we have typed values, things that are not necessarily equivalent. Here we have anything can be put after anything else, but that's not true for a category. And we'll see monoidal preorders have some illustrations associated with them as well. And it turns out that this side of it, through monoidal preorders and monoidal posets, have these sort of structure that can be illustrated, where we are combining successive things, and this will involve monoidal products associated with some of these combinations, like lemon, butter, and sugar here. But we'll also have an ordering that will obtain between the output from the input. And what this is saying is, as non-obvious as it sounds, lemon tensor butter tensor sugar tensor yolk is less than or equal to lemon filling. So you get lemon filling out of these things, and you sort of extract lemon filling from this. It's greater than it. You produce it from that. It has more things you want. So if you're interested in learning more about the diagrammatic representation, we're going to come back to it, but it probably won't be for a number of weeks until we've really tapped out adjunctions, monads, etc. So if you're interested in going down this side of things, I'd refer you to these videos, and I'd refer you to these as well, which talk about some of the application of this in a modeling context. If you want to see something about how this ramifies for functional programming, you can watch these videos on free applicatives and free monoidal functors, and this programming with categories lecture also speaks about this, and as does Bartosh's presentation here. So monoidal preorders will provide a point for growing our discussion of monoids. But free monoids provide this very nice illustration of adjunction, and gives an illustration of the ways in which you can get these homomorphisms between two very non-obvious things. The next lecture, we're going to be looking at a different application of adjunction associated with monads. And monads are going to sometimes have very interesting functors associated with them. For example, a functor to pair things up, or a functor to evaluate things. But they're also going to have some rich structure associated with the round trips, and what are called in the definition of adjunction eta, and associated with mu. Mu for collapsing things down, eta, and epsilon. So this could be co-unit and unit with eta corresponding to unit, and epsilon corresponding to co-unit, which are the result of round trips here, of sort of mapping over and mapping back. And those are going to be associated with monads. And every round trip will yield a monad or a comonad. And we'll be exploring that, and it will come out that true to this lecture, monads are associated with a monoidal category, and the monoidal category will have a bifunctor associated with turning a list of a list into a list, or a maybe of a maybe into a maybe, in a way that is observed in functional programming by join. So we're going to come back to that, but this is a bit of a teaser. If anyone's interested in going into the modeling side, you're welcome to, or the programming side more. That will be on our list, but probably not for another some weeks. Okay, so that's all we have time for today. I've taken you over time. Thank you very much for your attention, and hopefully this has reinforced some aspects of the basics of monoids, as well as giving you a glimpse of this intriguing adjunction between sets and free monoids. Thanks very much.
Thank you.
Thanks.
Thanks.